Hey, welcome back to the lecture. So in the previous lecture, we saw that when we changed the optimization level to 3, the code actually stopped working, isn't it? It is now not behaving as we expected. Now, the reason for this we have to find out, and for that we have to see the disassembly code generated for this optimization level. Okay, the code is same. So now let me just rebuild this, and let me just get into the debug mode. And so let me keep breakpoints here and here. Okay, now let me hit run. Okay, so here is a code generated. The first line is actually initializing of a pointer variable, isn't it? So here it is. The R0 is the pointer variable, and that is actually initialized with this address. Okay, so now let's see what happens when we execute this line. Yes, the R0 is actually filled with this value. Okay, so that is the address, isn't it? All right, fine. So now here what's happening? Now loading the contents of this address into R0. So that is taking place. That's fine. Okay, after that it compares. That's correct. And then here is a location where the instructions got changed. Now what's happening? Compare R0 with 0. So that means, so it is the instruction generated for this if condition, right? So that is if value is 0. Okay, so then continue with this while loop. If value is non-zero, then come to this while loop. Okay, so that's why here compare this with 0. Okay, if both are equal, okay, that means if R0 is 0, then jump to this location, the branch on equal. Okay, if these two are equal, then jump to this location. And when we jump to this location, we're supposed to read the content of that memory once again, isn't it? But look at here what's happening. It is not jumping here, it is jumping here. Okay, so that means the value of R0 is not updated. Okay, so that's the reason this application is not working. So these instructions are fine, no problem. So compare R0 with 0 is perfectly fine. Okay, so here it is. So for this instruction is generated. Okay, but instead of jumping here to update the value of R0 by once again reading the content of this memory location, it is jumping here. So that's the optimization the compiler has done for you, because the compiler tried to optimize your code by avoiding reading from memory again and again, right? So because memory reading operation, they need more clock cycles, and it is slow. Okay, so because it deals with the memory, right? So that's why, okay, in order to boost the performance, it actually avoided reading from the memory content again and again. So because the compiler somehow assumed that, okay, so I have read from the memory contents once and I updated the R0. So, and it assumed that the content of that memory location won't change in the lifespan of an application. This assumption may be good if this application runs on the desktop, let's say, where the content of that particular RAM location may not change over the period of time. But in embedded applications, that may not be true, okay, because some addresses are highly volatile in nature, right? For example, this address so may be updated by, let's say, DMA controller, or it may be updated by some other peripherals, right? So in those cases, this code will not work, right? Because here this address is highly volatile in nature. That means the content of this address may change at any time. And sometimes what happen is the address of the data register of some peripherals like UART, SPI, I2C, right? So those are highly volatile in nature because those registers receive data from the external world. So the contents of those data registers may change at any time when the application is running, isn't it? So that's why those addresses, that means the addresses of those data registers, has to be treated as volatile in nature. Okay, so now how do you solve this problem here? The solution is, tell the compiler that this pointer which is having this address is volatile. That means the contents of that address may change at any time. We can tell this to compiler by mentioning that pointer variable or variable as volatile by using volatile keyword or qualifier. Okay, so now let's see what happens when you compile this code and test it on the hardware. Let's see whether it works or not. Okay, so now I will keep a breakpoint here as well as here, and I will hit run. I'll remove this breakpoint and I will hit run. The code is running now, no problem. Now I will change the content of this. Okay, and here it is. Our application is indeed working. So now what's happening? Okay, let's analyze the code. Okay, so here let me keep a breakpoint here and hit run. Let me reset once. Okay, so here is a code which is updating R1. So now if I remove this breakpoint and if I just do single step, yes, R1 is updated here. Okay, and BEQ, branch on equal, R1 is compared for whether it is 0 or not. Okay, and now it is jumping to this location where it is updating R1 again. Okay, so that means the code is working now. So that means now we have instructed or forced the compiler to read from that address again and again. Alright, so now we have come to the end of this section, and in summary, how to decide whether to use volatile keyword or not. It's very simple. Whenever you are dealing with memory locations, then it's always better to use volatile keyword with that. Okay, whether you are writing to some memory location or reading from that memory location, then it's better to use volatile keyword with the pointer variable which you use in order to access that memory location. Okay, so not only with pointer variables, the volatile keyword can also be used with normal variables. Okay,